Today we talk about spectral theorem. This one is an important theorem for functional analysis. We also discuss today. First we start about statement of this theorem. We write this statement now. Suppose T belongs to compact operator from H to H and be self-adjoint. Then there exists a system of orthonormal vectors phi 1 phi 2 phi 3 phi 1 phi 2 phi 3 of eigenvectors of T. That means those are eigenvectors of T. Okay. And corresponding eigenvalues and corresponding eigenvalues lambda 1 lambda 2 lambda 3 such that norm of lambda 1 greater than norm of lambda 2 greater than norm of lambda 3. That means in increasing or in decreasing order, norm of lambda 1 less than norm of lambda 2 less than norm of lambda 3. Now then Tx equal to summation k equal to 1 to infinity lambda k x phi k inner product phi k for all x belongs to H if lambda n be infinite then lambda n tending to 0 as n tending to infinity. Okay, and the series on the right hand side converges in the operator norm of VH. That means bounded operator from H to H. Okay, this one is the spectral theorem. Okay, theorem will state about that if K compact operator from H to H and self-adjoint, that means adjoint of T equal to ST, then there exists an orthonormal system phi 1 phi 2 phi 3 of eigenvectors of T and corresponding eigenvalues are in decreasing modulus value order. Then Tx equal to summation k equal to 1 to infinity lambda k x phi k inner product phi k for all x belongs to H, and if lambda n be infinite infinite, then lambda n tends to 0, lambda n sequence be infinite, then lambda n tends to 0 as n tending to infinity, and the series on the right hand side converges in the operator norm of pH. Okay, then we're going to prove of this. We write proof now and proceed. Proof of this following theorem stepwise. We prove the following theorem. We prove the following theorem step by step. Okay. Then first we write here step 1. Construction of eigenvector. Construction of eigenvectors. Okay. Let you use theorem. Let h1 equal to h. Let h1 equal to h and t1 equal to t and t1 equal to t. Then by the theorem, then by some theorem, there exists an eigen value lambda 1 of t1 and an eigenvector phi 1 such that norm of mod of lambda 1 equal to norm of t1. Okay, now span of phi 1, now span of phi 1 be a closed subspace of h1, be a closed subspace of h1. Hence by the projection theorem, hence by the projection theorem, h1 equal to span of phi 1. Okay, then what we do, we erase our portion and going to forward of this proof. Now we write here hence by projection theorem, h1 equal to span of phi 1, here sum of span of phi 1 perpendicular. Okay, this one by projection theorem. Okay, that means we write here not just span of phi 1, h1 is represented as h1 equal to span of phi 1 and direct sum of span of phi 1 perpendicular. Let h2 let H2 equal to span of phi 1 perpendicular. Clearly H2 is a closed subspace of H1. Clearly H2 be a closed subspace of H1, and TH2 and TH2 subset of H2. Okay, then now let T2 equal to T1 H2 here. T1 restriction on H2, then T2 be compact and self adjoint operator in BH2. If T2 equal to 0, then there is nothing to prove. Then there is nothing to prove, and assume that T2 not equal to 0. Assume that T2 not equal to 0. Then there exists an eigenvalue lambda 2. Then there exists an eigenvalue lambda 2 of T2 with mod of lambda 2 equal to norm of T2 and a corresponding eigenvector and a corresponding eigenvector phi 2, okay, with norm phi equal to 1, norm of phi 2 equal to 1. Then since T2 is a restriction of T1, since T2 is a restriction of T1, okay, with norm of lambda 2 equal to norm of mod of lambda 2 equal to norm of T2 less than equal to norm of T1 equal to lambda 1, mod of lambda 1. Then y construction of phi 1 and phi 2, by construction of phi 1 and phi 2 are orthonormal, are orthonormal, okay. Then again we write, now let H3 equal to span of phi 1 phi 2 and clearly H3 subset of H2, and it is easy to show that it is easy to show that T of H3 subset of H3. The operator T equal to T restriction on H3 is compact and self-adjoint and self-adjoint. Okay. Hence, by theorem also it is a portion. Hence, by theorem. Hence, by theorem, there exists an eigenvalue lambda 3. There exists an eigenvalue lambda 3. There exists an eigenvalue lambda 3 of T3. Hence, there is some problem. How this problem occur, I don't know. Now all is clear, I think. Hence, by theorem, there exists an eigenvalue lambda 3. Okay, of T3 and a corresponding eigenvector phi 3 and a corresponding eigenvector phi 3 with norm of phi 3 equal to 1, and here lambda 3 equal to mod of lambda 3 equal to norm of T3, and hence lambda 3 less than lambda 2 less than lambda 1. Okay, less than equal to. And proceeding in this way, either after some stage of n, Tn equal to 0, or there exists a sequence lambda n of eigenvector. There exists a sequence lambda n of eigenvector there exists a sequence lambda n of eigenvalues of T, and corresponding eigenvector phi n and corresponding eigenvector phi n with norm phi n equal to 1 with norm phi n equal to 1 and norm of lambda n equal to norm of dn. So then also norm of lambda n plus 1 less than equal to norm of lambda n for each n. Now we're going to step 2. Okay, now we're going to step 2. If lambda n be infinite, if lambda n be infinite, then lambda n tends to 0. Then lambda n tends to 0. If lambda n does not tends to 0, then there exists an epsilon greater than 0 such that norm of lambda n greater than equal to epsilon for infinitely many n. If n not is equal to m, there exists t of phi n difference t of phi m square equal to lambda n phi n difference lambda n phi m square. Norm of this, okay, this one equal to lambda m square plus lambda n square greater than epsilon square. Okay, here 2 epsilon square, that means epsilon square. This shows that this shows that t of phi n has no convergent subsequence. This shows that t of phi n has no convergent subsequence. Okay, there is a contradiction. We erase that portion, then further proceed now. So what we get a contradiction. Okay, that means t of phi n has no convergent subsequence. This be a contradiction to the compactness of t, to the compactness of t. Okay, then hence we tell about that lambda n tends to 0 as n tending to infinity. Okay, so we also completed 2 steps, step 1 and step 2 also. Next we're going to forward step 3. Okay, step 3. Here we consider 2 cases. Here we consider two cases. Case 1, Tn equal to 0 for some n. Then let xn equal to x difference k equal to 1 to n x phi k of phi k. Then xn does not, then xn is perpendicular to phi I. Xn is perpendicular to phi I for 1 less than equal to I less than equal to n. Then 0 equal to Tn xn equal to Tx difference of k equal to 1 to n lambda k x phi k, here phi k. Okay. Then Tx equal to k equal to 1 to n lambda k x equal to x phi k inner product of phi k. Okay. Then Tn equal to 0 for some n and xn equal to this. Then Tn xn equal to this. Okay. So where then we also get this one when Tn equal to 0 for some n. Now we going to case 2. Okay. Case 2, if Tn not equal to 0 for some n. Okay. Or for infinitely many n. For infinitely, not some, infinitely many n. Then what happens? Then for x belongs to h, we have norm of Tx difference k equal to 1 to n lambda k x phi k inner product of phi k. Okay. Then this one equal to norm of Tnx, norm of Tnx n. Okay. Less than equal to norm of Tn, norm of xn equal to lambda n, norm of xn less than equal to norm of lambda n, norm of x tends to 0. Hence what happen? Then obviously, since lambda n tends to 0, then this one obviously tends to 0 as n tending to infinity. But hence what we get? Hence we get Tx equal to summation k equal to 1 to infinity lambda k inner product of x phi k phi k. Okay. So today we stop here. Okay, because we also discuss one important theorem, so we stop here.